Good morning again, and today is October 1st, so we are in a new month now. We are almost midway where we're supposed to be in terms of content, in terms of also the semester. We have an exam coming in about, I think, a little over a week from now. And so we should be ready for it. In terms of content, I think we have a lot of things. This week also we have 2 assignments in addition to the discussions that we have on a regular basis now. You got accustomed to them. Is the quiz and actually the homework that is assigned at the end of this week. So basically those are the 2 things. Please pay attention to the due date. I changed the quizzes. I think I made them a little bit less this time around in terms of number of questions, and I also allotted more time for them so that you guys would have a chance to basically think through those questions. Again, like all of the quizzes, you have 3 chances, 3 attempts basically. The highest grade is going to be the grade for the quiz. It is highly recommended that you take all of the attempts, even though probably you score high in one of them. The first one, for example, if you get 100%, it's still a good idea to do the other attempts because the questions change. So, and that should prepare you for your exam, as a matter of fact. So it's a good idea to take advantage of all of them. You're not going to lose any points. It's not like you average the points. So if you score very high in the first time around, you might risk to lose points on that. No. So it's a good idea that you take all of your attempts, take your time between the attempts to review the content so that you have a better chance to get to increasing the score if in case it was not good in the beginning. So this is really the items that you have. The assignments are due on or before October 10th, which is just before the exam. And so hopefully you guys will have time to go through those things and finish them. And if you have any difficulty, please let me know. In terms of content for today, we have to continue. Last time we started waves and talked specifically about sound and some of the properties of sound, which are common to almost all waves. And today we're going to talk, and that sound is actually an example of the so-called longitudinal waves, waves that travel in the same direction as their disturbances. So there are compressional waves for the case of sound, compressions followed by rarefications, and they propagate in the same directions where these compressions followed by rarefications are happening in the same direction, okay? Today is an example of a transverse wave, okay? And from the get-go is going to be about light, of course. And from the get-go is going to be the electric field and the magnetic field oscillating in space. They don't need actually to be propagating in matter. As a matter of fact, matter hinders them basically when the electric field and the magnetic field hit a specific atomic structure, for example, and if their frequency happened to be the right frequency, the electron or the atom or whatever that is going to absorb that particle of light. And then, for a moment, light is not traveling while it's being absorbed by matter. And then, of course, the atom or the electron or something get excited. So they want to go back to their ground state. They want to go back to where they were originally. So in this case, they emit light. While light is traveling between an atom is still traveling with the same speed, which is 300,000 kilometers per second. So in matter, light tends to slow down a little, okay, because of the fact that during short periods of time, it's being absorbed by matter itself, okay? Other than that, light travels in vacuum with the same speed, which is 300,000 kilometers per second or 300 million meters per second. And later on, we will find out that actually it's an upper limit. There is nothing that can travel faster than light. And as I said before, I said 2 words. I said the fact that light is a wave, which is basically the topic of the day. And what is waving in this case is the electric field and the magnetic field in tandem. They work with one another. They're not 2 different entities. They're only one thing, okay? And they're electromagnetic. Basically, an electric field and a magnetic field, they are 2 sides of the same thing, okay? You look at it on one side and it looks this way. You look at it on the other side, it looks the other way. But both of them are actually one thing, Okay. Now, they happen to be oscillating in a 90-degree angle between one another. So that's basically what is waving. So if somebody asks you, okay, light is a wave, that's fine. What is waving? What is basically oscillating? In this case, the answer is an electric and a magnetic field, both of them joined together, okay? They're inseparable. Now, I used another word also, that when light particles hit an electron, for example, they're absorbed. And particle, as I said before, it's not in a wave. So is it a wave or is it a particle? And that's a trouble, okay? It's both. We're not going to delve too much into this one, but it's actually light can be thought of also of particles, the so-called photons, particles of light, okay? The only trouble with these particles, they don't sit still. If they stop, they don't exist. So the only way for these particles to exist is that they have to keep on moving with the same speed, which is the speed of light. So while they have been absorbed, they completely are gone. They don't exist anymore. The minute they are released back by the atom, that's when they appear again, and they appear as particles of light. So light has this dilemma, which is it doesn't know which one it is. So if somebody asks you, for example, okay, I did an experiment on this object, and it tastes like an apple. It weighs like an apple. It looks like an apple. As a matter of fact, the shape of it is like an apple. It smells like an apple. So everything I did for it passes the test for an apple. Therefore, I conclude it's an apple. Somebody else, and the same person actually, I did another test on this object, which is the same object, that the one that I determined already to being an apple. I did another test on this object in terms of the taste, in terms of color, in terms of texture, in terms of smell, and in terms of weight, and in terms of size, and it determines it's actually an orange. So am I holding an orange or an apple? The answer, because both experiments are correct, it is actually in a sense, in the same time, an apple and an orange, okay? So that's where the confusion might be sometimes. So light is a particle and a wave in the same time, okay? So to give it an example with an orange and an apple, it's actually an orange and an apple in the same time, okay? It may be confusing to us at this level, but that's what light behaves, okay? That's how it behaves. It behaves both, okay? So let's get into the topic of the day. So I know that probably some of your students, especially if you're going to be teaching and things like that, you're going to be asked with this, some of these questions. So the simplest answer, it's both. Okay, it's a wave. So what is waving? It's the electric and the magnetic field. And if somebody else who reads a little bit more and they found out about the concept of a photon, so it's a particle also. Okay, it does both. So let's get into the topic of the day. The whole perspective of chapter 11 is actually being a wave. Okay. So the whole thing in here, we're talking about the wave nature of light. Obviously, light was a puzzle for us humans from the get-go. We didn't know what it was. Okay, we wanted to understand what light is. So people tried to understand it and tried to measure it. So we know for a sense, for a fact, for example, if I have a candle and I lit the candle, light starts to emanate from it, starts to come out from it. Okay. As I move further away, I still see the light, but it's going to start to diminish. If I move very far away from it, I see it a dot probably in space, and if I move further away, I will not be able to see it at all. As a matter of fact, if I'm sitting very far away from it, okay, a mile away, for example, from the light, and my friend takes the candle and turns it, lights it, I'm going to see what he did. I'm going to see actually the light. I probably will not be able to see him or her in the dark, mile away, especially pitch dark in the old days, but I'm going to see for a fact the light that is coming from that one. So light must travel in space, okay? So how fast light travels, that was one of the problems that people early on tried to determine. So light was a puzzle from the get-go. We know, for example, if I stand in front of a pond, I see the reflection of everything I see above the pond. That's one thing. I mean, I see, as a matter of fact, the trees and the birds flying above the pond and everything that is above the pond, I can see an image of it underneath, except it's upside down. I mean, the tree is pointing down Everything else is pointing. As a matter of fact, if I lean on the pond, I will see myself too on the front of the pond. I see an image of myself. Not only that, but I can actually see this object enter the pond. I can see fish, for example, swimming. I can see other things. And that has to do with light, because of course has to do with how we're going to see this object with our own eyes. Okay. So at night we don't have any light, so we don't see anything. During daytime we see objects. So that's basically some of the questions that people struggled with and tried to understand at the beginning. First of all, what is light? How fast it moves? And these properties of reflections and refractions and all of these things basically for light that it does. So that is basically what we're going to try to explore in this thing here. Historically, it went through a lot of processes. First of all, one of the early experiments that was tried to measure the speed of light was by Alhazen, and he tried to, but he actually postulated that light actually must travel super fast because objects in the sky are very far away, and actually before him, the Greek school, because they were puzzled with the issue. Okay, if the light has an infinite speed, if light travels instantaneously from point to point, there should not be a difference between day and night, because daytime we have the sun, but during nighttime we have the stars too. So if the light is coming from every which way to us, night and day should be the same. But stars are very far away, so light cannot be traveling instantaneously. So it has to have a speed, but we didn't know how to measure it. We know that it has, they knew that it has a speed, but there was no experiment to measure it. The first attempt at it was actually Galileo, okay? Or it is documented attempt to it was Galileo. What he did was, he had a lantern, and he had his friend going about a mile away from him, actually about the distance, and he told him, okay, I'm going to light my lantern, and when you see the light from the lantern, light yours, of course. So he measured the distance. He knows how far they are apart, and if he can find the time between his lantern for the light to travel from him to his friend, and from his assistant back to him, so he knows the distance. Basically, take that distances divided by the time. And of course, he didn't have a clock at that time. He used his heartbeat. Actually, he used his wrist, okay, to measure the time. That's how he did most of his experiments. He didn't have a clock or anything like that. So the point being in here is, he collected a lot of data, and then he called his friend, and they came together next to one another, and he repeated the experiment. He found the numbers do not differ from one another. So he threw away the data, and he realized that was not a good enough, basically, experiment, because what he realized what he was measuring was actually the reaction time of his friend and himself. So he dismissed the data, so it was not a good measure for the speed of light. The first really serious number that we got from the speed of light had to do with Romer after the discovery by Galileo himself, among other things, of the moons of Jupiter. And one of the moons of Jupiter was Io, which takes about 42.5 hours to go once around Jupiter. Okay. So Mr. Romer did the following. He measured the period, the time it takes for Io to go once around Jupiter, and because Jupiter is very far away, it takes about 12 years for 1 year on Jupiter, 12 years on Earth for 1 year on Jupiter. So if I wait 6 months later, Jupiter would have hardly moved in its orbit because it's very far away. So if I remeasure again now the period of Io, I should be shifted. I should see it shifted because of the fact that Earth is on the other side of the sun. So light now is taking an extra distance, which is the distance between the Earth and the sun twice, which is about 150 million kilometers times 2. That's about 300 million kilometers for light to reach us when we're out on the other side. So he recalculated, and he found the speed of light to be almost, to be very, very high, of course. He found it off by almost 100,000 kilometers per second. He found it to be 200,000 kilometers per second. But that was the first serious, basically, measurements of light using astronomy. Then after that, Fizeau used a different experiment, actually, and in which he had gears spinning, and he shone a light through the gear, basically where it breaks down, okay, through the teeth of the gear, and it reflects off of another surface and bounces back. Now, if the gear is spinning super fast, there could be a timing where light can go straight through and come back without having to basically go through any other part. So he adjusted the speed of the gear fast enough, measure the distances, the delay in between the reflection and back and forth, and he was able to find a much, much closer value to the speed of light than Mr. Romer, to the current known value. Piso's experiment was further basically refined, and now we know light travels with 300,000 kilometers per second. As a matter of fact, it's 299,000, almost 300,000, slightly less than 300,000 kilometers per second. So that was basically part of the idea behind it in terms of determining its speed. Well, we knew about the reflection and the refraction. That's one thing. That actually one of the things that was documented by the Greeks was the refraction of light on the surface of water. So this is something that we knew. I mean, so those two experiments, they can be explained. And there was also the work of Mr. Alhazen that later on was refined by Mr. Newton himself about that light is probably made of particles, and those particles, when they hit the surface, they bounce off of it. And that's basically, you can explain the law of reflection and refraction. So that was something, the optics, okay, the things we see with our own eyes. So that was really the start of the science of optics. And people then theorized, hey, light must be made up of tiny particles that we can't see, but they are there, okay? And optics works perfectly, and still today it works beautifully. I mean, all of these glasses, all of the devices that we have on a regular basis, lenses and mirrors and telescopes and cameras and eyeglasses and things like that, they are all based on the science of optics, and it's a very powerful science. It's really a lot of people, that's what they do, I mean, for their on a daily basis. Now, Mr. Young in the early 1800s did an experiment with light and determined that if I have a source of light, the same color, monochromatic light, basically blue, for example, and if I split that, basically what he did, he had a surface, which is an opaque surface. It does not transmit light on the other side, but it has two openings in it. Excuse me. Two openings are very close from one another. So light, when it passes through those two openings, it says the same light, actually, that came from the source. And now you have two new sources. And those two new sources hit another surface where you collect the light, basically, that it's coming from these two sources. This is called the double slit experiment. If you probably read about it, it's popular in science fiction. It's also popular among philosophers and among a lot of people. So this is the beginning of it. The 1920s experiment was done on particles, done on electrons, actually. But this one is the wave, the one that was done by Mr. Young in the early 1800s. So in here, when light is collected, he noticed the interference patterns. We said from last chapter, if you see interference, you know you're dealing with a wave. So Mr. Young, based on the separation between where the double slits exist and where the plate is, based on that distance, based on the angle where the interference patterns are shown, where the maxima and the minima are, he was able to determine the wavelength of light. We didn't know then what was waving. We have no idea what was waving by the early 1800s, but we were able to find its wavelength. Since we know its speed, we can find its frequency also. So we have the properties of the wave, namely wavelength, the speed of the wave, which is the speed of light, the frequency, the period, and everything else that you would want to think of. Intensity is how bright it is. So we have everything about the wave, but we have no clue what was waving at that time. It took the work of Mr. Maxwell toward the end of the 1800s, as a matter of fact, who collected a lot of the work of Mr. Faraday and Ampere and Coulomb and a lot of other people, Lenz and everybody else who worked on that, and put them together, and he found the flaw in one of the laws of Mr. Ampere, actually. He corrected it, And he put them together and he solved them, and he realized, hey, electricity and magnetism and optics, namely light, and the experiments of basically what Mr. Newton did and everybody else did before him, and everybody, it's all one thing. It's all indicating that it's actually the electric field and the magnetic field that are oscillating. So that was a major, major, major achievement that Mr. James Clerk Maxwell did. In a sense, he unified a lot of work of the people before him and put them in one theory, in one thing. Where light now and optics and wave, the nature of light, and the work of Huygens and everybody else, and leading to basically all there is just in few equations that he was able to describe. And that's what we knew then, that Mr. Young's experiment was actually describing the waves of the electric field and the magnetic field, and what we measured before in terms of wavelength and frequency was that of light. And light is just a special case of a big spectrum, where now you have lights that have longer wavelength, namely infrared and microwave and radio waves. They're all actually another form of light, but they happen to have very long wavelength, shorter wavelength, including ultraviolet light, and also X-rays and gamma rays. They're also part of the same band. And light happened to sit just on a narrow band on that thing. So that was a major achievement. Mr. Hertz later on did more work on the, especially the telecommunication part of it, and how to basically design antennas and things like that. And that's really how the name of frequency was changed from 1/2 to Mr. Hertz's work. So that was something. Of course, the story did not end there. Mr. Einstein later on took some of the work that they were working on, namely that if you shine light on a surface, photons are ejected, and this is basically what some people have on their houses now for the solar panels, basically, and generating electricity was light, and that has to have particles again, and that's where the photon came back to existence. And Mr. Einstein actually won his Nobel Prize not because of relativity, but because of his work on the same thing. You see. Now that was the story of light, which still not completely, it still has this two, is it an orange or an apple? The answer, it's both, okay? So this is a little bit of history for you guys. Hopefully it gives you a little bit of perspective on how much work that was in there. The story of light is really the story of science, especially physics, okay? That's how things evolve, and technology in general. Without it, a lot of things would not have happened till today. So this is what we're going to cover in this chapter. The fact that light is an EM spectrum, part of the EM spectrum, okay? So the words EM in this case stand for electromagnetism. That's where Mr. Maxwell actually, that's his major contribution. He unified everything, okay, into one thing. Then we'll try and talk about the opacity of objects. Objects tend to be opaque, basically not transmitting light for certain frequencies, and transparent, namely transmitting light for other frequencies. And this has some major implications in terms of the so-called greenhouse effect. Because especially glass, for example, or even the atmosphere does the same thing, or all materials do the same thing. For the atmosphere, for example, it's completely transparent in terms of the light itself, basically, the one that we call light, the frequencies that we see. And that's why we see objects beyond the atmosphere. That's why we see the sun, for example, and we see the stars, and we see the moon and objects beyond our atmosphere. If we happen to, for example, survive a landing on Venus and we look in the skies, we will not be able to see anything in there. We'll see fuzzy things as far as the sun, and everything else is pitch dark or at night, even because you can't see the stars. I mean, because this atmosphere there is super thick and you cannot see it. But in here on Earth, this is our atmosphere. Transparent to light. But then, when the Earth absorbs that light, it overheats, basically, becomes hot. So it does not emit it back in the same form. It does not emit it light. It's going to emit it in a wavelength that is actually in the infrared. In infrared, now the atmosphere is actually not transparent for it. It's an opaque. It's going to reflect it back. Actually, it's going to come back to the Earth. and that's bad, okay? So, as a matter of fact, it does not even absorb it. They're going to reflect it back. And so the infrared then is going to be trapped in here, and the infrared is also called heat, okay? The wavelength is high enough so that it agitates the molecules in the atmosphere, and the molecules, when they are agitated in the atmosphere, that is what the temperature is. That's how we feel as heat. So in other words, it's going to result in an increase in temperature. Then we're going to talk about the laws of reflection and refraction, okay? Those, they have a name in science. They're called Snell's laws. Mr. Snell did a lot of work on these things in here. I mean, they were not discovered by him, of course, both of them, as a matter of fact, but because his contributions were tremendous in this area, that they called them after him, at least some of the literatures they do, okay? And then the concept of color. What do we see when we see color? Again, this is our brain. This has very little to do with the actual electricity and magnetism and how light is actually the electromagnetic behavior. It all happens in the brain. And that's why it's relative, really. So when I see something blue, I have a very specific notion in my head what blue look like. There is no guarantee that two people will have the same depth, intensity, and if you wish, hueness or whatever that is. The actual color itself is a brain interpretation. And that's why actually it varies from person to person. Some people, they completely have no notion exactly of the color blue or red the way that you perceive it and I perceive it. Or at least what we think we are commonly perceiving. We probably are perceiving different things. To the point that they look at it and they distinguish it no more than a gray color, okay? And those are the people who are basically classified as colorblind. But again, we all have a different level of interpretation of this color. So this is something that happens on the level of the brain. Obviously, it's a little bit complicated. But in terms of us in here, we can take two different colors and mix them together, and I can say that it has changed to this color. You with me agree on your interpretation of that very same color, that it has changed on that color. So there is some common sense too. So there is some commonality in all of this, and this is what we're going to explore in this area. Then we're going to talk about dispersion, which is one of the properties that is used, especially in terms of science, for example, when we're trying to analyze light. And because light turns out to be a signature of specific compositions in the matter that emitted them. So dispersion later on plays a major role in trying to determine structures, what is made up of, okay? So we use that, we shine light on specific material, and then later on when it comes out on the other side is dependent on the structure. But we're going to use it in a very simple case to begin with. We're going to take the case of the prism, when basically light, white light, is shone through that. And then depending on the frequency, light is going to be broken down into different angles. It comes out basically with different colors from the prism. And as an example, of course, you have seen probably some of those known pictures for the different, for the formation of the rainbow, okay? And how come rainbows form when there is rain far away, or at least there are droplets of water in the air? So that's something that we experience day in, day out, okay? As a matter of fact, there is rainbow, and there are some times when you're lucky enough, you can see the second one, the double rainbow, and the colors will be reversed in a double rainbow environment. Now and finally, we're going to talk about polarization. Polarization is actually a useful concept. It turns out of the two fields, the electric field and the magnetic field that compose light, our eyes are more sensitive to the electric field than the magnetic field. As a matter of fact, the magnetic field does not move charges. I mean, so if you have electrons sitting on the hairs inside your retina, there are some fine structures in there, and the electric field comes in. So if the electric field is pointing upward, the charges, which are negative charges, they move downward, okay? So they start moving up and down depending on which way the electric field is. So the concept of polarization has to do with which way the electric field is pointing. So if you take light that is unpolarized, going in all directions, and you make it go through a filter, basically, where only that component of the electric field comes in from the other side, now you have it polarized, okay? And this is what is used by drivers, when they put those sunglasses when they're driving, the vision is kind of fuzzy when you're driving and the sun is coming at a certain angle. The minute you put those polarizers, now you can see clearer because all of a sudden the other components are eliminated and now you can see the direction where you're headed. The funny part with these polarizers, you can cancel light altogether by just having two polarizers that make 90-degree angle between one another. They put one polarizer in one direction and you put another polarizer in the opposite to it. So this one the second one cancels the first one and now you don't see nothing. Okay. So that has some interesting applications, especially in terms of technology and sunglasses and things like that. But again, you can also use it for studies of light more specifically to determine already you know which direction the light is coming at. Okay, so this is in a nutshell what your chapter is all about. It took us about half an hour to go through the slide, but I promise the next slides will not be that long. So, again, light and electromagnetic waves. Okay, the word is only one word. Okay, it's made up of two, but it's really one word. Created by vibrating electric charges having frequency that fall within the range of sight. That is because our brain evolved over a long period of time to have this range that we're in. So what makes light to begin with is charges in motion. So if you have an antenna that is transmitting, for transmission, that antenna has charges that are moving up and down along its length. And while they're moving up and down, they're going to emit electric field and a magnetic field in the same time. Okay. Now, far away from that antenna, those same electromagnetic fields that were created, waves, they keep on traveling to reach the antenna that analyze them, or the eye, or whatever object that is going to be collecting them. Case in point, stars that are very far away from us, sometimes millions of thousands of light years from here, sometimes galaxies that are actually millions of light years from here, we can still see them because of the same thing. Their ions or their charges that far away from us, but their effect is coming to us, traveling all of that empty space and arrives to it. Okay, so no charge traveled that distance. It's impossible for the charger to travel that distance in that amount of time, because no matter what, they cannot be traveling with the speed of light. So if light takes 1,000 years to reach us, the particles themselves, they would take a lot longer than that. Okay. So, and again, the frequency with which the charges are going up and down determines the frequency of light that is emitted from these sources. Okay. Of course, the speed of light, I already mentioned the fact that it's 300,000 kilometers per second, or 300 million kilometers per second. Light itself, sound itself is 340 meters per second, or 0.34 kilometers per second. Of course, this number is huge compared to the other number. Okay, so it's almost a million times as fast. Okay, so light is super fast. That's why in the example we did last time, a person sitting far away and a person sitting closer from the singer, the person sitting far away will have the same sensation provided the distance is close enough. Of course, sitting 45 meters away from the singer is very close compared to the singer where you are on the other edge of the earth, basically, when light goes around the earth and comes back to it. And that's basically the difference between the two. Okay. So that is the speed of light, 300,000 kilometers per second. Again, I already mentioned the fact that light is an electric and magnetic fields. The electric field, actually, and a magnetic field. The red one is an electric field, and the blue one is the magnetic field, okay? And they're in sync, meaning when the electric field is maximum, the magnetic field also is maximum. When the electric field vanishes, so does the magnetic field. Both of them vanish. Again. It happens only in your class, by the way, this recording stops. I don't know. Something is funny, I think, in my router in here. Sorry about that. Okay. Anyway, the magnetic field and the electric field, they make a 90-degree angle between one another. So they're at right angle with one another. They don't oscillate in the same direction. That's one thing. While they're oscillating perpendicular to one another, they travel in a direction perpendicular to both of them. Okay? So both of them travel perpendicular to the direction of the travel. Hence, it's a transverse wave. Because the direction of oscillation, whether the electric field or that of the magnetic field, is perpendicular to the direction of propagation. Okay? That is why it's a transverse field. A transverse wave, I'm sorry. Transverse wave. Transverse wave because the electric field and the magnetic field, both of them are oscillating, first of all, perpendicular to one another. And second of all, they're oscillating anyway. So as I was saying before, the electric field and the magnetic field, they are perpendicular to one another. You have to really remember that part. It's critical to the whole thing. And as they are moving in the direction perpendicular to both of them, as per the right-hand rule. Okay, if this is the electric field and if this is the magnetic field, this is the direction with which they are moving. I'm sorry. If this is the electric field, this is the magnetic field, and this is the direction with which they are moving. So they are moving like this. Okay, so that's the direction of the right-hand rule. So if the thumb points where they are moving, the electric field is, I don't know, this is the index, and then this one is the middle finger, and then whatever you guys want to call them. So as long as you have that understanding, this is the direction with which they are moving. So here is the challenge for the day. I want you to really discuss this point in here because it's critical on how light travels, okay? So it's given by the right-hand rule, okay? So the electric field, the magnetic field, the symbol for the magnetic field is B, by the way, okay? And this is the direction of propagation, travel, okay? So that is the point in here. So the question is, how does light travel? It travels, first of all, it's a transverse wave, such a way that the electric field and the magnetic field are perpendicular to one another, and they oscillate perpendicular to the direction of travel following the right-hand rule. Do you want me to guys write these things in here down for you guys?
Yes, please.
Okay. So light travels in a direction perpendicular to both the electric. I'm separating the words in here because actually they are, okay? And the electric and magnetic fields, because when we do measurements on both, we find that we have an electric field and a magnetic field, albeit they're joined, okay? The electric field and magnetic fields, which are perpendicular to one another or normal to one another, both. Okay. As a matter of fact, I really want you guys to put it in your own terms. How is that? Okay. So I'm going to put it in here to one another, following or using the HR. Okay. So if you're left-handed, I'm sorry, doesn't work for you. Okay. So that's how the question is, and that's the answer to it. Again, we talk about the spectrum and the fact that we have light that is basically just a portion of the entire spectrum. So when Mr. Maxwell solved these equations, and actually Hertz looked at it too, and that's when the equations indicated that light is just a portion of that, okay? So actually there were some suspicions to begin with, and before the work of Mr. Maxwell and Hertz, that light is probably no more than just an EM wave, okay? So this is the spectrum. Light is just this tiny portion of everything. That's what we see. That's what our eyes evolved to seeing. So it's the range between 4 times 10 to the power 14 hertz and 7, between 4 and 7 hertz. But the frequencies can get very, 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 very low to only 100 hertz, okay, of wavelength that are a kilometer long. So these are very long wavelength, 1 kilometer wavelength, okay, to waves that are super high, 10 to the power 24. Between 10 to the power 22 and 10 to the power 24 is a huge difference, okay, big range. Of course, these are very, very energetic. The energy goes this way, by the way. The higher the frequency, the higher the energy, okay? The more damaging this radiation can do. The wavelength is 10 to the negative 5 nanometer. Remember, a nanometer is the size of an atom. This is even 1/100th of that, okay? So we're talking about things that happen in the inside of the proton itself, or the nucleus itself. So these things, they can go inside your, not just damage the atom or the molecule, which is a big deal. I mean, if they happen to have, they're dealing with a DNA, for example, where these guys can go, where this, the ultraviolet can go. Actually, the ultraviolet, they can go even shorter distances than that. I mean, longer distances than that. So this is the X-rays. Actually, the X-rays are working on the level of the atom. They can take your electrons and basically strip you off of electrons, and they can burn you, basically. So the X-rays can be damaging big time. The first thing the technician does when you go to the hospital and he or she takes the X-ray reading for you, he tells you to stand, don't move, and then he runs away. Boom! And here, so with a given amount of X-ray radiation. The only good thing about it is the fact that you're not exposed for a long period of time for this radiation. Otherwise, this is a very, very damaging thing. So you don't want to stick around for long there, because he or she lives there. That's part of their daily job. So if they stick there, they're going to be exposed for that radiation for a long period of time, and they will suffer the consequences. So that's because these things can be very, very deadly. Okay. Gamma rays are even more. Gamma rays are actually worse. Okay. That's really what the in terms of radiations or gamma rays, they can go inside and destroy the nucleus of your atom. So that's really they are far more energetic. Ultraviolet, they deal with the basically the skin, because the molecules in there, they're actually, and they can cause cancer because they start to deform basically the elements, and now you have problems in your skin, and that's really damaging, not just for humans, for all life basically. We evolved to deal with violet all the way to the red color. And the spectrum starts from violet, then you have the blue turns to light blue, then the green, and then the light green, and then the yellow, and finally orange, and then red. So that's what our eyes are basically sensitive to. That's what our brains tells us, okay, that these frequencies are. For every single frequency we associate a specific color. After that, it's dark color again. It's black color again. We don't see it, okay? As far as us is concerned, it doesn't exist. And this is where the infrared is. This is where below red is, okay? And then you have the microwave region, and then the radio region, radio frequency, which are very, very, like I said, long wavelength and less energy. So the energy, as you can see, increases this way, okay? So being exposed to a higher frequency for a long period of time, and even for short period of times for this kind of energy in here, is very, very damaging. So you don't want to be near it. Yet if you go to one of those basically laboratory, you will see that we have a lot of radiation, including some gamma radiation coming from the cosmos. Unfortunately, most of it is not coming to the surface, so we can deal, I mean, at least life in general can deal with that, okay? So the EM spectrum spans waves ranging from lowest to highest frequencies. The smallest portion of the EM wave is that of the visible light. Is very narrow. Okay, very narrow. The band there is very narrow. Okay, at least this is our classifications. This is how we classify them ourselves. Okay, maybe for different creatures, for dogs, for example, that we know that they don't see color, is probably they are seeing it, but maybe in a different range that we are accustomed to. But they see this region. Okay, they respond to it. So order of increasing frequency. So you have to ask yourself, what are you talking about? Either wavelength or frequency. So frequency is higher from which side? Red is the lowest frequency. Violet is higher frequency. Okay, nearly twice the frequency of the red. Ultraviolet, this is what causes sunburns. X-rays are even higher. Gamma rays is the highest frequencies that you can think of. Okay, we don't know of any other frequency that probably can exist. Maybe before the Big Bang, yes. Is this smart? Photographer wishes to photograph a lightning bolt by setting a camera so that it is triggered by the sound of thunder. This is a bad idea. You don't want to go outside when it's lightning, okay? Don't do it. Especially with a camera and you have high points in it, that's not a good idea, okay? Because there is an electric discharge there, and that electric discharge finds the nearest point for it to go to the ground. And if you happen to be standing in there, you are a conductor, so you're going to be exposed to it. Okay. Again, I talked about opacity and the fact that materials, I mean, right now, if you look outside on the side of your door, not the window, don't use the window, okay? Look, you know, probably there is a trees on the other side. There is probably something else with a neighbor. Maybe there is something, but you can see nothing through the doors because the doors are opaque as far as the light is concerned. If you look through the window, you can see things again because the visible light goes through the window, and that's why you can see the trees on the other side of the window, okay? Except that there are some frequencies that are not transparent for light, for example, the infrared and the ultraviolet. So frequencies that can penetrate and can. That's why we are lucky enough here on Earth to have the atmosphere, because the atmosphere actually acts as a shield too, because it's really preventing other frequencies from entering the Earth, especially those of high frequencies. That's why the Chandra telescope and other telescopes, they ended up deploying them above the atmosphere because they're supposed to operate at higher frequencies, and they cannot be useful for astronomy if they're below the atmosphere. So, and it's protecting us, okay? So that's really some of the properties of the, and especially in case of the ultraviolet radiation, is the ozone layer. It plays a major role in terms of absorbing these radiations. So again, this is part of the properties of light, that in terms of absorption and in terms of being reflected back, okay? So at this point, this is a macroscopic description. This is what we see, okay? On certain object, it reflects on certain objects, absorbed and goes through to the other side. So in terms of what's going on, basically, as I mentioned before, it's similar to the phenomenon of resonance. So basically what happened in here is light is absorbed depending on its wavelength, okay? Depending on how short or long it is. which part of the atom gets excited? Is it the entire molecule if it's a very long wavelength? Or is it the atom if it's a shorter wavelength? Or if it's the electron itself in a specific atom, if it's even shorter wavelength that is in the visible light? That's why our eyes are sensitive, because it's actually, it moves with the electrons, okay? Or is it even shorter wavelength that even the electrons themselves tend to go inside the atom, so inside the nucleus itself? So depending on the wavelength, now matter will absorb that light. Of course, now it's excited. It's no longer sitting where it was before. It's not necessarily in where it was before. Here is the model. You have, for example, for at least the visible light, you have an electron in here sitting. This is its ground state when it's normal, okay, before being excited. So light comes in here, and now it moves it because it's absorbed it. Now it's more excited. It has more energy. So it has to jump to a higher level, okay? So depending on the frequency, the jump could be very high if it has absorbed a very high frequency, more energy, basically. It gained a lot of energy. Obviously, there could be transition regions that it has skipped because of the fact that it had gained more energy than just jumping to the next level, jump to at least 2 or 3 more levels. But now it wants to go back to its ground state. So there are 2 possibilities, for example, for this specific electron. It could go to the next level, but when it goes to the next level, it's not going to emit as much energy as it gained. It's only going to emit some of that energy. Hence, the wavelength is going to be longer. The frequency is going to be less. So in here, let's say, for example, the frequency that came in was looking like this. Now, when it emerges, it's going to go like this. So it's a very long wavelength. Let me try to redraw it. It did not draw the whole thing. So this is how the wave looked like. It's not as packed as the first one. It didn't have a lot of punch, okay? And then it's going to move to the next level, emitting probably something similar to this one, not the same value, but something also long wavelength, probably longer or shorter, depending on the jump. So in this case, that's exactly what's going on with the Earth. It absorbs light, which is a high frequency, and when it emits it back, it's not going to emit it at high frequency, it's going to emit it at low frequency. So when it's emitted back, it's absorbed in this form for the glass, and then when this material absorbs it, it's going to emit it in this one, which is very long, so it's going to bounce back, basically. It's going to stay there. So that's, in a nutshell, what the greenhouse effect is. So again, this is just a model, okay? The atom is observed. The atom now is excited. It wants to release it. So now it's released. It goes to the next atom, is absorbed by it. Now it's excited. It's going to release. The next atom will take it now again, and so on and so forth until it's transmitted. As I said before, light travels at 300,000 kilometers per second in vacuum. And space between atoms or molecules is vacuum. So while it's traveling between an atom and an atom, it's still traveling with 300,000 kilometers per second. But during the time while it's being excited, the atom that is, the light is absorbed. It's not going anywhere. So that's why the light appears to be slower. But at the end, if the object is transparent, it's going to be transmitted back out, okay? So we're going to see it again. So light, 300 million meters per second, or 300,000 meters per kilometers per second. That is in vacuum, actually, or in air, because it's very close from the air, okay? Atmosphere slightly less than C, but rounded off to be C. So in air, it's roughly about 300,000 kilometers per second. In water, it's 3/4 of that, okay? In glass, it's 2/3 of that. And in diamond, it's almost half the speed of light. So basically, depending on the material. Some materials, there is zero transmission because they're opaque, completely opaque. Again, here is the word photons. That is what I said before. Photons are actually particles. They have mass, albeit that mass is equal to 0 when they're stationary. That means they don't exist when it's not moving. while they are moving, they actually have a mass that you can calculate, and that mass has to do with the frequency. Okay. So strictly speaking, the photons of light incident on glass are also the one that travel through and exist on the other side, not the ones that travel. No, they're emitted, because once they're absorbed by the material, by the electron, for example, they're gone. It's the electron now, when it jumps back to the same level that it started from and gives you the same frequency, it's going to create a new photon for you. Okay, we still have about half an hour. Okay, so the law of reflection and refraction, again, the law itself is this one. And I know it was part of the discussion from last week. The angle of incidence, which is the angle made by incoming light with the normal to the surface. Okay, that is the angle of incidence, and the angle of reflection, it's the same thing. The angle made by the outgoing ray with the normal to the surface. In this case, we have a flat mirror. Okay, flat mirror basically produce a replica of the image. Everything else works except the left right. Everything else is conserved. Height is conserved. So if this was an inch high, this will be an inch high. Okay, the image basically, if you are standing in here, okay, and looking at the mirror, and look at your toes, for example, your toes appear to be coming from the other side in here. Okay, I'm sorry, appear to be coming from the other side to your eye. Of course, it's a reflection of this light coming to you, but as far as you're concerned, here it is. You look at your head, for example, and it appears to be, because the ray comes in and bounces back, and appears to your eye that it's on the other side. You look at your hand, for example, and this is the ray, so it appears to you it's on the other side, okay? And so on and so forth. So you have made a replica using Snell's law. This is Snell's law, number one, okay? This is the law of reflection. So again, everything else is conserved, and there is no object on the other side. This image is virtual, not real. How do I know it's real or virtual? If I bring a film, for example, and see if it develops, and put a film in here and expose the film, nothing will come out of it. There will be no image. So the image in this case is a virtual image. Okay? Not real. Okay? And it's upright. In other words, the head looks up and the feet look down. So it's an upright image. And in this case, the magnification is 1. In other words, the size is the same. Magnification is 1. All of these terms are critical when you're doing optics. When trying to use lenses, for example, to make an object appear bigger or not, you were wondering whether or not the image is inverted or upright. You were wondering if the image is real. Can you put a film on the other side? For example, for this lens, the image is going to be on the other side. Okay, I can't put a film in here, and actually it's going to develop. And that's exactly the principle behind the cameras. In the old days, they put an actual film, they expose it. Once the film is exposed, it's going to have a replica of the image. The only problem with those is the image is inverted upside down. Okay, that's actually what's happening in a retina, because there is a lens in front of your eye that takes the image. Everything that you're looking up to it is actually inverted in your retina. The brain fixes things for you up. Otherwise, you will have trouble walking, because you think that you will be walking upside down. You will be walking on what you think is up and then down. So the brain fixes that. There was an experiment that was done on people. Actually, they took a lens with no magnification whatsoever, the same lens. All it does is it inverts the image to the eye, and they gave it for basically subjects to test them. Now, since the image is inverted by the lens of the eye will invert the image one more time, and now the image, at least on the retina, is sitting straight. It's sitting upright. Now the brain, what it does for you is going to revert it. When it reverted it, people had difficulty walking initially. It took them a long time for them to adjust. And the brain, basically what it did was something mysterious. It fixed itself. The images that normally are inverted for them, now it tells them that they are right, that this is how, and they started walking again normally. So they removed the lenses for those people, and now people had difficulty, and the brain adjusted itself again to work. So this is kind of some of the things that is working in there. So that's really one of the things about the eye, because the eye has a focal, has a lens, and the lens has a focal distance, and the image has to form exactly on the retina. Some people have short eyes, and the image does not form on the retina; it forms behind the retina, and they need corrective lenses because they need to bring the image so that it forms there, at least a sharp image to form on the retina. Some people actually have the other way around. The problem, basically, some people are farsighted than nearsighted because the image is not forming on the retina either before it or after it, and that's why you need corrective lenses and the right ones to put the image where it needs to be. So again, this is a little bit of optics and how the eye works, which is a very complicated device, but it has to do with this optics. Obviously, this is a flat mirror, and as I said before, left and right is the only thing that is not conserved. Everything else is conserved. Magnification, namely the height, and everything else is the same. Okay. Here is mirrors. In this case, it's a convex mirror. Okay. I'm sorry. This is two kinds of mirrors. Okay. This is a convex. This is a concave mirror. Okay. The way to tell is one of them is looks like a cave, concave, and the other one is convex, so it's the opposite to it. So again, in here, the magnification is less than 1. You see, the image in this case is less. That's why you see on the side of the car, on the right-hand side, objects appear closer than, or appear further than they appear, or something like that. They're warning you because objects trying to give you a big, broader view, okay? So they are closer than what they appear. And here, it's the opposite, okay? So again, you can lose this combination of mirrors to form images, and the image depend again on the curvature of the mirror. Again, this is image formation using mirrors, but you can also use lenses, and lenses, they come in a different varieties. I mean, there are at least 2 convex and concave mirror lenses, but they're a combination of both because they have bending on both sides. So you can have convex and concave, you can have convex and flat, and the optics is a fascinating science and technology that is really a lot of things going there, especially if you're into astronomy and photography. And even if you are not, probably just as a person who sells glasses, I mean, that's an interesting topic, or eye doctor, okay? Again, diffusion is when you're dealing with wavelengths that are of the same order of magnitude now on the deformation in the surface. So in this case, you have an incoming monochromatic parallel, basically, ray, like for example, coming from a laser pointer. When they hit the surface at that point, the rays will go in every which way. Okay, so again, that has to do with the every single point in here, Snell's law is observed. So if I take this one, this is the incoming ray, this is the outgoing ray, this is the normal to them. The incoming is equal to the outgoing. Same thing in here. Okay, so every one of them, but the outgoing now overall appears to be diffused, appears to be going in all directions. This is a parabolic antenna. Parabolic antennas are used extensively to focusing or diffusing light, depending on which way. Is it transmitting or receiving? If it's receiving, it's actually focusing all the rays as it bounces to them to a single point in here, where the LMB now collects this light and send it through a signal that is analyzed later on, okay? If it's transmitting, it's the other way around, but then it's going to transmit in every which way. At least for initially, it's going to be parallel, and then it starts to diffuse at the end. Okay, I think we are short on time, so probably refraction is another law. Again, refraction has to do with the with 2 surfaces. So you have a medium in here where light has a speed, and here and you have a different medium where light travels with different speed. So light appears to us to be coming from this source. Okay, so if I'm looking at the pond and I see a fish, it looks to me like the fish is here, but in actuality it's in here. And because there is also another law for the law of refraction, and it has to do with this. This is the incoming, this is the outgoing, and this is the angle now of refraction. Okay. So again, wavefronts, they break down in the surface and they give you the illusion of objects. You can do this experiment, as a matter of fact, with a glass and a coin, okay? Put a coin in a glass, move away from it, empty coin, and add water to it. And you will see, as you will add water, because the rays coming from your eye going to the surface of the water and now breaking, the glass at some point, as the water starts to fill, you start to seeing the quarter or the dime inside or a nickel inside, okay? The penny, if you put a penny in the inside the bottom and then you add to it, this is an interesting experiment. Again, it has to do with the law of refraction, okay? This is what I was talking about in terms of the fish. So apparently birds, at least the one that fish, they have learned the trick. They have taken optics. They know exactly where the fish is. So when they land on it, they go and grab it and fly. So I imagine somewhere in the bird society, there is a school where they learn optics. I don't know, okay? Again, this is part of the illusions. This is an illusion. This is not the real thing. Of course, you have to be careful with that. Otherwise, most time you're going to miss the fish if you go by your first intuition. Same thing in here with the sunset and the sundown. When you're looking at the sky and the sun has the rays coming from it, this is the horizon, okay? Anything below the horizon, technically you can see, but the sun has already fallen below the horizon in the evening. It's already past sunset. Sundown. So the ray is coming from, or it's sunset, the same thing, okay? So the ray is coming from the sun. Now it's refracted on the atmosphere, and it gives you the image. So for you, you think the sun is just setting down, but it actually, or is coming up, but it actually has already is still below the horizon because of this law of refraction. Now, this is some of the reasons why the sunset and the sundown actually appear. We're going to talk about the frequency. That's the dispersion law. That's why the sky appear blue during daytime and appear orange in the evening or in the morning. Again, this is an illusion also due to the fact that the atmosphere is hot underneath. Okay, then the upper layers of the atmosphere. So again, as rays is coming, it's going to be refracted, and as it's refracted, it gives you the illusion that the object is actually, you think that there is an image on the other side below. So that is actually the mirage, okay, that you see, and you think that sometimes that there is water, but it's just a reflection of the sky in there. When you get there, you don't see any object in there. Okay, the concept of color again has to do with the wavelength that has emitted it in this case. So it looks a different color depending on the light. This is something, again, visual. This is our brains basically sometimes messing up, doesn't really understand how colors really are. For us, if we are at night, during daytime, we're doing an experiment with the light from the sun and we conduct it on specific frequencies, we can interpret that color specifically. But if the light source changes, our brains play a trick on us and give us a different sensation of colors. And in the lack of color completely, then we see the object has no color, and as if it changed. That's because it's reflecting light that has fallen on it, that's all. Case in point, for example, if I look on an object and think that the object has a specific color, to me this object appears blue, and I have a specific sensation for it, because it's absorbing everything except the frequency blue that is reflected back to my eye, and my eye is deciding that this is blue, whereas this one is actually deciding that it's red. And again, I'm looking at it in here physically, and I'm looking at it at the screen. It appears different versions of red from the screen to the, at least for me. Probably you guys have a different perception of these colors. Again, it's the reflected frequency. All the frequencies are being absorbed except the red. This one is absorbing everything, okay? It's not transmitting anything back to me. If I have this one in here, it's transmitting everything. It appears white to me. So the color white doesn't exist, okay? Again, there are some rules on how you mix colors and you get the specific colors, and you can, okay. And here is the theory behind it. Again, put green and red and you get the yellow. Put the green and blue and you get the cyan color. Put the blue and red and you get the magenta color. and put them all together and you get the white color. And this colors in here, the magenta, the cyan, and the the yellow, are part of the colors. For example, on your printer, that's what you do. You put them, mix them together, and you can make as much colors as you want. The prism, as I was talking about, depending on the wavelength, the shorter wavelength get less refracted when they emerge from the other surface than the blue frequencies, and that's why the colors are separated. So this dispersion is frequency dependent, depends on the wavelength actually, and that's how basically the rainbows are formed. So rainbows are formed because of the droplets of water in here, and droplet of water is just like a prism in here, except it uses both refraction and reflection in the same time. So you have light that is coming, it's going to be refracted, then it bounces off using Snell's law, and then it's going to be refracted one more time, and your eye now see them broken down, okay? Of course, you have to have two droplets for them to merge in a specific point and make different colors, but for you, there are so many droplets in there, they combine to give you different separation of colors as they're emerging from the rain. And here is the point I was talking about, okay? So because of this 2-degree separation, for the violet, it comes at 40 degree. For the, for the red, it's at 42 degree from the original monochromatic, for the original light, which is all lights coming, okay? So they are in here, white light. As it emerges, it's broken down with that 2 degree separation. Now your eye is seeing basically the objects in the sky as they are separated from the violet all the way to the blue. The violet will always appear bottom and the blue appears higher. In a double rainbow, it's flipped backward. Okay. So here is the red higher. Here is the blue lower. And in double rainbow, it should really appear backward. The blue is higher and the red is lower. Okay. So this is, let me see here. We have the polarization, which is a very important concept. It has to do, as a matter of fact, with the electric field. And I already mentioned the fact that the polarizer will force the electric field to oscillate in a specific direction versus another polarizer in here. And so light that is not polarized, like this one in here, it has all directions basically for the electric field. Sometimes when it's completely polarized, then the electric field has a specific direction, okay? If this is the electric field, for example, this could be the magnetic field, and so on and so forth. But in polarized light now, it's completely in one direction, and you can use polarizers in this case to force the light to be in one specific direction. Now, light sometimes can do weird things. It can be circularly polarized. That means that it can actually go around in a circle as it's moving around. It could be spiraling, or actually spiraling not in a specific circle, but in some sort of an ellipsoid shape. And it could be also basically not polarized completely, basically in random directions, or polarized in a specific direction. A polarizer, basically what it does is you have a source of light in here that is non-polarized. When it emerges off of it now, it's going to be a vertical component is polarized. And the second polarizer basically just takes it and makes it more. So there is an analogy with string in here. The second polarizer now, if you flip it at 90-degree angle, now at this point you end up with a completely nothing. It looks dark. Okay. So here is the illustration for that. Okay, you have two polarizers in the same direction. Now what she did was she flipped them again, and basically she's combining all kinds of polarizers in here to make different colors or different. So polarization only works for transverse waves. So that's the other question of the day. Okay. You cannot use it for longitudinal waves. Longitudinal waves, you cannot do polarization. So we have two questions of the day today. This one and the one before it. Are we good? Everybody? So you have...
Was A the answer?
Yes, it's transverse waves only produce, can be polarized, okay?
Okay.
You cannot polarize because the idea behind it is that the transverse wave and the direction of propagation as the wave is coming to you, now you have specific direction that emerges off of it. Longitudinal wave, now you cannot polarize it because it's in the same direction. So if you polarize it, you're going to cancel the whole thing. Okay, so there will be no wave coming off of it. Okay, so those are.
Oh, sorry. So A was the answer, and then you said there was another question too.
Yeah, we had a first question which has to do with the right-hand rule, basically, and the answer was it's how light travels. It travels in
So
a
it's the one in
direction.
the chat.
Yes, yes.
Okay.
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 Okay, guys, you have 2 assignments at least for this week in addition to the discussion stuff, and the 2 should be on Canvas. The quiz should be available in a few minutes. As I said before, the quiz is 40 minutes and it's only 18 questions, so please take your time and do it right. Okay, Sherry, you have a question for us? You have no microphone. Microphone is not working and the video is.
I got it. Can you hear me now?
Yes.
Sorry. So my question, I missed the first couple minutes of class, and when I jumped on, I know you were talking about the test that's coming up. Could you just go over the couple things?
The test is going to be on when is it? The exam supposed to be the 13th, isn't it? Yes. So what I'm going, yeah. Okay, again, I don't hear you. So it's going to be available for you for an extended period of time. So it's going to be available at night and it's going to be due in the morning. So it's going to be chapters again that are listed in there. Actually, there will be more communications, more details in terms of the exam because we still have another chapter before we're tested on it. Okay? So there will be more details. For right now, what I want you to do is we have chapter 12 that is coming on Tuesday next week. And after that, we're ready for the exam. Of course, we will have another chapter past that point, but we should be ready for this exam. So there will be more communications and details about, you should have more time though. That's the only thing that is different in there. And I will not be holding a live session during the time because it's going to start at night and then end in the morning. So I cannot have the Zoom session open the entire time. Okay?
Okay, so the exam is not for a while.
The exam is not next week, the week after.
Okay.
So we still have time.
And are you going to do some type of a study review like you did last time?
Yes, I'm going to post that, yes, for you guys. Okay?
Okay, perfect. Thank you.
Okay. Okay, so I'm going to stop the recording.